So we've been talking about black holes, and we've been talking about black holes and the weird things that happen in space near a black hole due to general relativity. Well, an interesting thing about general relativity is general relativity has survived many theoretical challenges and tests. Einstein proposed it right away. They tested it by measuring the displacement of stars in the sky, at least the apparent displacement of stars in the sky, the bending of light due to the gravity. So that was the first test. They've tested it using atomic clocks, the gravitational test. Gravity does actually change time. We've actually verified that gravity does create a gravitational redshift. That was also predicted. They were also able to discover that you have the stretching of space due to black holes. That too has been detected. It has also been measured. Gravity Probe B proved that for sure that with Earth. And then the Kerr metric using general relativity also predicted that you would have this measurable effect due to frame dragging. That too has been detected. The only part of general relativity that was not detected was that Einstein said that there ought to be these gravitational waves. And that is that if you have two objects with gravity and they're moving around each other, or even they're moving, they should produce distortions of gravity traveling through space. Well, distortions of gravity just create distortions of space going away. So you would have spatial distortions moving away. And so this would be most evident if two really massive objects were rotating around each other in a very short time frame. So it'd be like two black holes or two neutron stars orbiting each other very close together. Okay, so that's what you would expect. So gravitational waves. And so for years, physicists have been trying to measure gravitational waves. The idea finally came into fruition after many attempts in the idea that maybe our detectors weren't good enough. And so they built these detectors that would be basically two giant paths. So one giant path that goes for miles one way, one giant path that goes miles in the other direction, and then basically in the middle of it putting something like a Michelson interferometer. That Michelson-Morley experiment we talked about, that interferometer would be able to detect if one of these paths changed lengths. So you could put that in there and measure this effect. And so as a gravity wave goes by, for example, a circle would change shape kind of in the little diagram down here in the lower left. And so that would be the idea is what we'd be looking for. Now, obviously, gravity waves aren't going to make that obvious of a change in shape as they go by. But if you had a sensitive enough detector, you should measure something. So they started building these detectors. They still didn't measure anything. And so they said, well, maybe the detectors still aren't sensitive enough. So the LIGO facility, one of them was built in Hanford, Washington, one in Louisiana, and LIGO stands for Laser Interferometer Gravity Wave Observatory. And so the LIGO facility was constructed, these two things, and again, it was like a Michelson interferometer. It's just waiting for a gravity wave to come by and change the length of one of these paths, and these paths are miles long. Well, the thing is that the light would go down one path, hit a mirror, come back, hit a mirror, come back, and go back and forth many times. So even though it's miles long, it acts like it's maybe thousands of miles long. And so that makes it more sensitive. They also, so they set this thing up, and they didn't detect anything. They said, well, the problem is it's too sensitive to stray things happening. So there's too much stray noise from the Earth. There's seismic distortions, you got traffic noises, even people talking, that would change the path length. So they had to isolate everything in these giant isolators to make sure that nothing other than a passing gravity wave would do anything. And so they upgraded the facility, making it far more sensitive and far less sensitive to anything any other non-gravity wave influence. And within the first week of operation after the upgrade, it found a signal. Okay, and then the signal was analyzed, and then what happened was a number of months later they announced it in February of 2016 that they found the signal, and both detectors found the same signal. And that's important because if it went through just one of them, that's probably not due to a gravitational wave. So this wave comes through, and then all of a sudden they both detected, and so it most likely was due to a couple of black holes that were orbiting each other and spiraling inwards. Now, as these waves go away, they carry energy with them, and so that energy makes the orbit of the two black holes get closer and closer together, so they actually spiral into one another and merge. And then once they merge, so as they're spiraling together, the gravity waves get bigger and bigger and bigger, and then they merge, and then the gravity waves go away. And so that's exactly what they found. And so this was a fantastic discovery. Over the next few years, they started finding more of them. Okay, and then Italy started building gravity wave detectors. Other gravity direct detectors have now become active, and since then we found a couple dozen, or more than 2 dozen of these things, these gravitational waves. And so this was the final proof of concept of general relativity. This was the only thing that general relativity had predicted that we had never found before. And so these gravitational wave detectors are now the next line of telescopes that are possible. So now we have a new way of telescoping the sky, or a new way of studying the sky with gravity wave telescopes. And as we get better at not just detecting them, but finding out where they come from and what's going on, this gives us a new probe of the universe. And so gravitational waves, again, from general relativity. We've actually detected several of these events coming together. So we have a black holes coming together, and even what looks like two neutron stars merging. So we've actually got a huge wealth now of black hole detections. And so we have X-ray studies that found a bunch of black holes, and then we have the gravity wave detectors, and then they're finding other kinds of black holes and neutron stars and so forth. And so now we have more and more evidence of black holes. Okay, and like I said, neutron stars also coming together.